Right, so welcome to 7.2, the binomial distribution. Here we have a couple of images. The first is Jacob Bernoulli, the discoverer or person that kind of came up with this type of distribution. And the other is a picture of actual binomial distribution. Hopefully it looks familiar, and we'll kind of come back and review that image later as well. Right, so we have to talk, why is Bernoulli important to binomial distributions? He's the person that came up or founded the idea of Bernoulli trial, which is a repeated independent trial measured in terms of success or failure. So is it favorable or not favorable to the outcome that we want? And he lived in 1654 to 1705. All right, so for rolling doubles, either we get doubles or we don't get doubles. That's our success or failure. For manufacturing widgets, so if a widget is anything you produce at a factory, either it works or it doesn't work. Success or failure. It's black and white kind of idea. Okay, so a Bernoulli distribution, or binomial distribution, is made up of Bernoulli trials. All trials are independent and identically distributed, so the two trials affect each other, and they have the same distribution each time. So we have independent, as I said, as outcome of one trial does not affect the other. Identical, probability of success is the same. Okay, again, we still have the random variable RV, and we use capital X. So at this time, the random variable is the number of successes in a given number of trials for that binomial distribution. Okay. So in general, probability distribution for binomial looks similar to what we've seen in chapter 5 with the binomial expansion. Surprise. Okay, so the probability of x is equal to n choose x times p to the x, q to the x. P is the probability of success, q is the probability of failure, x is the number of successes, n is the total number of Bernoulli trials. And of course we also have the expectation, which can easily be calculated by multiplying n and p. N times p. Okay, so an example, say we're rolling a pair of dice. We're going to be successes, doubles, failures, non-doubles. So probability of success is 1 over 6, and probability of failure is 5 over 6. Our random variable is the number of successes, so the number of doubles. So in this case, we're going to roll it 5 times, and so n is 5, and so our question is, from 5 rolls of the dice, what is the probability of getting 3 doubles? So n is 5, r's, or x is 3, p is 1/6, and q is 5/6. Okay. Back through. If you look really closely, you'll see that those solutions and the probability of x equals 3. So we have 5 choose 3, 1/6 to the 3 power of 3, 5/6 to the power of 2. Calculate that if you want a fraction, which is always nice. 125 over 3,888, or as a decimal, 0.03215. So just a little bit more than 3% probability of getting 3 doubles out of 5 rolls. Apologize